Okay, so here we're asked to compute cosine of the fourth x by making use of our reduction formulas above. And we're going to see comparatively this is, well, kind of a lot easier. You just have to have your reduction formulas to do it. So cosine reduces down to 2 powers smaller by using this formula. So let's take a look at that on our cosine of the fourth here. Okay. So the formula is cosine, so integral of cosine of the fourth would be cosine of n minus 1. So that would be cosine cubed x times the sine of x. All of that divided by n, so n was 4, okay, plus n minus 1 over n times the integral of cosine n minus 2, so that drops us down to cosine squared. Okay, cosine squared we can once again apply this reduction formula to. Okay, we can once again apply this reduction formula. Okay, so let's take a look at an example here. So that would be 3/4 carrying through and applying the reduction formula for cosine squared. That would be cosine 1 power smaller. So cosine to the first power times sine. All divided by n, which in this case is 2. And n plus 1 over n, 1 over 2. Integral cosine to the 2 minus 2, which would cosine to 0, which would be 1. So that would just be dx. And so putting this all together, cosine cubed x sine x, all that divided by 4, plus 3/8 cosine x sine x, and then 3 1/4 and 1/2 would be 3/8 x plus a constant. So we have this result here. We have this result here, which looks quite different from our other result. Right, which looks quite different from our other result, 3/8 x plus 1/4 sine of a double angle plus 1/32 sine of 4x. But if you were to work around with some identities, you should find that these two things do in fact turn out to be the same. We could again manipulate these using trig identities to eventually try and drive inequality, or you can see here I've actually graphed these two functions, and when I turn one off, you can see if I turn the blue one off, the red graph and the blue graph do lie on top of each other. Now it is possible, and there's a potential chance here that you could end up getting something like this with these doing it one way, where it's shifted up. Because remember, when we do the indefinite integral, it's plus a constant. A constant can be anything. So they could be, the graphs of these two functions could be off by a constant, as long as the rest of the shape of the graph is the same. Now that doesn't happen here. There is no off by a constant. They actually do lay right on top of each other, again, as you can see looking at the graphs. So an interesting thing you might want to challenge yourself to is to see if you could somehow transform these over from one form over to the other. A nice little challenge for yourself to kind of try that, to see, can I show that this thing is equal to this thing over here. Again, I've shown you graphically, it sure looks like they are. But a challenge would be to see if you can transform this stuff over into this stuff. Now, of course, you notice you already have the 3/8 x, and you have the 3/8 x, so that part's taken care of. So you'd really be just looking at, can I take this stuff here and transform this stuff into this stuff, or vice versa, Okay. So that's something you might want to challenge yourself with, just to have a little practice there to see if you can do that. But again, that's just if you want to. Okay, but we can see though the big thing here, and then is these reduction formulas are way quicker and way more efficient than doing it the other way. That's why they were developed, was to give us a way to kind of speed this process up some. Okay, so that's what the reduction formulas were developed for, and that's why we use them, because they do make it a lot quicker